De Morgan's theorems are two simple but powerful rules that tell us how not, the complement, interacts with and or operations. In plain English, they say colon. The complement of an and of several variables is the same as the OR of the complements of each variable. A bar dot b dot c dot 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 equals a bar plus b bar plus c bar plus dot dot dot. The complement of an OR of several variables is the same as the and of the complements of each variable. A bar plus b plus c plus dot 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 equals a bar dot b dot c dot dot dot. Think of a group of door switches that all have to be on to let the light shine, and if you want the light to be off, you can either make any one of the switches off or of the not switches. The theorem just formalizes this everyday intuition. Explanation: a truth table lists every possible combination of input values and shows the output. To verify De Morgan's first theorem, we build a table for not A and B and one for not A or not B. The rows are: first row, a 0, B0, A and B0, not A and B1, not a 1, not B1, not a or not B1. Second row, a 0, B1, A and B0, not A and B1, not a 1, not B0, not or not B1. Third row, a 1, B0, A and B0, not A and B1, not a 0, not B1, not a or not B1. Fourth row, a 1, B1, A and B1, not A and B0, not a 0, not B0, not a or not B0. The column for not A and B matches exactly the column for not A or not B. Therefore, the theorem holds. Doing the same for the second theorem, not A or B equals not A and not B, gives identical columns, confirming the rule for all possible inputs. The visual match of columns is like checking that two different recipes always give the same taste for every possible set of ingredients. Explanation: algebraic proof uses only the basic Boolean identities. Identity: x plus 0 equals x, x times 1 equals x. Null: x plus 1 equals 1, x times 0 equals 0. Complement: x plus not x equals 1, x times not x equals 0. Distributive, and the fact that double complement not x equals x. Proof of the first theorem: not a b equals not a plus not b. Step 1. Start with the left side and multiply by the Boolean identity 1 equals b plus not b. Not a b equals not a b times open parenthesis b plus not b close parenthesis. Step 2. Distribute equals not a b plus not a b not b. Step 3. Use idempotent law b equals b and complement law b times not b equals 0 equals not a b plus not 0. Step 4. Complement of 0 is 1 and x plus 1 equals 1 equals not a b plus 1 equals 1. This step shows the expression always results in 1 when a b equals 0. To finish the equality, we apply the consensus theorem or more directly use the definition of complement. Not a b equals not a plus not b. The intermediate steps can be rearranged. Most textbooks present a shorter route by applying the complement law twice. Proof of the second theorem follows the same idea, starting with not a plus b and inserting a times not a equals 0 to split the term, eventually arriving at not a times not b. The key insight is that Boolean algebra lets us insert do-nothing factors like x plus not x equals 1 or x times not x equals 0 to reshape an expression until it matches the desired form. Digital hardware often prefers a single type of gate because it simplifies manufacturing. NAND and NOR are called complementary gates because they are the not versions of AND and OR. De Morgan's theorems give the exact relationship. A NAND gate is an AND gate followed by a NOT. Using the first theorem, the NAND output can be expressed as an OR of inverted inputs. NAND of A and B equals not A and B equals not a plus not B. So a NAND behaves like a wired OR of the complements of its inputs. A NOR gate is an OR gate followed by a NOT by the second theorem. NOR of A and B equals not A or B equals not A and not B. This shows a NOR works as an AND of the inverted inputs. Real-world analogy: think of two security cameras A and B. A NAND alarm rings when not both cameras see motion. This is the same as ringing if either camera does not see motion or of the no motion signals. A NOR alarm rings only when none of the cameras see motion, which is the same as requiring both no motion signals to be true and of the no motion signals. Thus, the theorems let designers replace an AND plus not with a single NAND gate and an OR plus not with a single NOR gate. De Morgan's laws are extremely handy for cleaning up logic equations, especially when you want to eliminate not signs from inside the expression. Consider the expression f equals not of a and not b plus c. Using the first theorem on the outer not. Apply not xy equals not x plus, not y f equals not a plus not of not b plus c. Now handle the second not with the second theorem not x plus y equals not x, and not y f equals not a plus b and not c. Now the function contains only one not on the variable a and an and inside the parentheses. A much simpler hardware implementation. Another practical use is pull-up, pull-down logic in microcontroller code. Suppose you need a condition that is true when neither button X nor button Y is pressed. The natural description is not X or Y. De Morgan tells you this is the same as not X and not Y, which matches how you usually read two independent not pressed signals. Thus the laws let you push nots outward, turning complex nested inversions into a flat set of gates that are easier to wire. Explanation: sum of products, SOP, form is a big OR of smaller AND terms. Product of sums, POS, is a big AND of smaller OR terms. De Morgan's theorems allow you to flip between them by complementing the whole function. Given a function in SOP, say, f equals a b plus c bar d. Take the complement to f bar equals not of a b plus c bar d. Apply the second theorem, not of OR becomes AND of nots. Equals not a b times not of c bar d. Now each factor can be turned using the first theorem. Equals open not a plus not b close times open c plus not d close. The result is a POS expression for f bar. If you need a POS for f itself, simply complement again, double complement, or start from a POS and apply the same steps. In practice, this conversion is used when a designer prefers NAND only, SOP, or NOR only, POS implementations. By swapping SOP and POS with De Morgan, you can pick the gate library that fits the cost or speed requirements. When you only have NAND or only NOR gates available, De Morgan's theorems give a recipe to build any inverted function. Example 1, implementing a simple not using NAND. A NAND gate with both inputs tied together behaves as a NOT. NAND of A and A equals not A. Example 2, realizing the AND function with NAND only. First NAND the inputs, then NAND the result with itself. AND of A and B equals not A and B, which is NAND of A and B with NAND of A and B. The inner NAND gives not AB. The outer NAND inverts it back to a B. Example 3, building an OR using only NAND. Use De Morgan. A plus B equals not a plus not B. Implement the inner knots with tied input NANDs, then NAND the two results. First, not A equals NAND of A and A. Second, not B equals NAND of B and B. Finally, a plus B equals NAND of not A and not B. Example 4, using NOR only to get an AND. Apply the second theorem. A and B equals not a plus not B. First, not A equals NOR of A and A. Second, not B equals NOR of B and B. Finally, A and B equals NOR of not A and not B. These constructions show that any Boolean function can be built from just NANDs or just NORs, which is why modern ASICs and FPGAs often use a standard cell library of only these two gate types. A real-world picture. Think of a kitchen that only has a blender. By feeding the same ingredient twice or mixing in a clever order, you can still make a soup, a sauce, or a puree. The blender, which represents NAND or NOR, is the only tool, but De Morgan's theorems are the recipes that tell you how. These questions illustrate how De Morgan's laws are used to prove identities, change forms, and build real gate-level circuits. Exactly the skills examiners look for. Sample exam question 1. Question: prove that not open bracket A plus not B close bracket and C equals not A and B plus not C using De Morgan's theorems and basic Boolean identities. Step 1. Apply the first theorem to the outer not of an AND. Not open bracket A plus not B close bracket and C equals not open bracket A plus not B close bracket plus not C. Step 2. Apply the second theorem to not open bracket A plus not B close bracket. Not A plus not B equals not A and not B. Step 3. Double complement gives not B equals B, so the expression becomes not A and B plus not C. Thus the expression is proved. Sample exam question 2. Question: convert the sum of products expression f equals not a and b plus a and c to an equivalent product of sums form using De Morgan's theorems. Step 1. Complement the function. Not f equals not open bracket not a and b plus a and c close bracket. Step 2. Use De Morgan, not of or becomes and of nots. This gives not open bracket not a and b close bracket and not open bracket a and c close bracket. Step 3. Apply the first theorem to each term. This becomes open bracket a plus not b close bracket and open bracket not a plus not c close bracket. Step 4. Complement again to obtain f equals not f, which is not open bracket a plus not b close bracket and open bracket not a plus not c close bracket close bracket. Apply De Morgan one more time, not of n and becomes or of nots. This gives not open bracket a plus not b close bracket plus not open bracket not a plus not c close bracket. Apply the second theorem inside each knot. This yields not a and b plus a and c, which matches the original sum of products. Confirming the product of sums we derived for not f, the final product of sums for f is open bracket a plus not b close bracket and open bracket not a plus not c close bracket. Sample exam question 3. Question: design a NAND-only circuit that implements the function g equals open bracket a plus b close bracket and not c. Step 1. Write the function using only NAND primitives. G equals open bracket a plus b close bracket and not c, which equals not open bracket a plus b close bracket and not c close bracket. Step 2. Apply De Morgan to the inner knot, not of n, and becomes not open bracket a plus b close bracket plus c close bracket. Step 3. Now each knot can be realized with a NAND fed by the same signal. Not open bracket a plus b close bracket equals NAND of a plus b with a plus b, but first we need an OR using NANDs. Or via De Morgan, a plus b equals not of not a and not b. Implement not a as NAND of a with a, and not b as NAND of b with b. NAND those two results. NAND of not a and not b equals not of not a and not b, which is a plus b. Then NAND the OR output with itself to get not open bracket a plus b close bracket. Step 4. Finally NAND the result of step 3 with c, since c equals NAND of c with c gives not c, and we need plus c inside the knot. The expression becomes g equals NAND of a plus b with a plus b, and c. The resulting schematic uses only NAND gates and follows directly from De Morgan's theorems.